And I would like to introduce Erik Meijer. And before he tells his perspective on his work, let me tell a little bit about Erik's and my background. So we actually worked together in Europe, I don't know, 15 years ago on functional programming languages and program transformation. And we met at conferences, and then we didn't see each other until we met in, I think, in a mind swap in year 2000. And one of the problems at this mind swap was that there's actually a business group within Microsoft, Web Data, whose only concern is to move data between the different worlds of relational databases and object-oriented systems and XML back and forth. And so one of the questions at this mind swap was, can we actually do better? And together we started a little project. Actually, we typically met for lunch in order to address that problem. And we came up with a reasonable solution, which actually then was later picked up by Web Data. And Erik Meijer moved as an architect to Web Data, and since then is pushing LINQ forward, together then later with Anders, who joined us, and the SQL team. And I think he will tell us more about what has happened during the last 3 years. Thanks a lot.
Okay, well, thanks a lot. So yeah, so this talk is also a little bit about how a crazy guy from a crazy programming language research guy can then end up in product teams, you know, selling the stupid ideas from, you know, 20, 30 years of programming language research. So as Wolfram said, this is kind of the problem I've been trying to solve since, you know, the last 10 years, I think. And this is kind of the 50,000 foot version of it. So a typical kind of distributed application looks as follows. You have some data in your database. You want to suck that out into the middle tier, where you want to do some computations on that data. Then you want to create some presentation of that. Typically, that is, you know, done using XML or HTML. Then you get back the results. You want to do some validation or some more computation. That computation is done using objects. And then you want to push back the results to the database. So what you see here is that you have typically kind of 3 types of data: tables of rows, graphs of objects, and trees of nodes. But, you know, on purpose, these slides are unreadable. Because if you try to read that, and if you try to write programs like this these days, this is what happens. You know, it's very bad for your hair, because it's extremely brittle. So, for example, in order to get data from the back end into the middle tier, you're sending strings that represent SQL programs over there. So there's no real kind of program. No, you send strings, then you get back some untyped result set that you then have to kind of, you know, mess around here. And then the same thing here. In order to create HTML or XML, you do that by creating strings. So it's like we haven't evolved since TickleTK, where strings were the universal glue. So this is, you know, it's really horrible. And I'm to be honest, I'm pretty sad that the state of the art is a monster. Okay, so anybody that tries to write these distributed 3-tier applications will end up with some really funky-looking monster. So I've been kind of working for, as I said, for 10 years to try to solve this simple problem. And as Wolfram said, you know, Erik V0 or maybe V1. I believed in functional programming, pure, declarative, all that, blah, blah, blah. So what I set out to do is to say, let's take Haskell, which is, you know, really the only pure language around, and try to use that to solve this problem. So what we did is we built something called Haskell DB, where you could do queries in a nice typed way using monads. I will say a little bit more about that. Then we had on the middle tier, we had something to write business logic. We had something called Haskell server pages. And then on the client side, we even had a Haskell interpreter running in Internet Explorer, such that you didn't have to use JavaScript, but you could use Haskell all over the place. So this worked well, except for the fact that the world's population of Haskell programmers fits in a 747, and if that 747 crashes, nobody would even notice. So even though this is a theoretical, beautiful solution, the biggest problem is selling this to the world. And even people here that are using functional programming, they are not using pure functional languages. They are using ML or OCaml, which are impure, strict languages. And here I was like Mr. Purity, doing monads, effects. Didn't work. So then I thought, well, let's continue and move to industry. Okay, but that's what I'm going to tell you later about. Let's go back into the history. Because if you look back in the history, you see that even this Haskell stuff wasn't new. Because if you go way back to the 70s, people were doing this kind of programming already. If you look at languages like Settle, and then, you know, Darlington and Burstall and so on, they were writing programs using ZF expressions, using set expressions. And that was something very old. And then Phil Wattler, who is the master in taking kind of, you know, arcane theory and then applying that to functional programming, which is for most people as arcane as that theory, but still, for the functional programmers, this is really applied, and took that stuff and said, look, all that stuff here can be generalized to something called monads, and using this you can model the relational calculus. So in the programming language world, in the functional programming language world, there's a long history of kind of going from this theory into practical application, but the missing link is now to take this from the world of the theory of functional programming and make it available to the masses. So in the end, you will see that I end up with Visual Basic, because that's what I mean with the masses. I want to make this stuff accessible to the common programmer. Okay, you don't need a PhD in computer science. My mother-in-law should be able to use this stuff, not knowing that she's doing deep mathematics and using monads and monoids and whatever. Okay, so what are these list comprehensions? Okay, so this is an example here. So you write, you know, give me all the x's where x's are drawn from the set 1 to n, where n modulo x equals 0. And if you know SQL, well, you kind of close your eyes a little bit and you see that it's select from where, okay? Select x from this collection where some predicate. Okay, it's just a kind of slightly different notation. And then you can write some functions here, and here now I can write, give me all the p's where p is drawn from 2 to n, where p is prime. So here's this very simple program that uses these comprehensions that were invented, well, by the mathematicians kind of even further, right? But by the computer scientists in the 70s. And then probably the mathematicians, I think, 1800s or something. That was before I was born, so I don't know. But anyway, these comprehensions, they look nice, but they're nothing more than syntactic sugar over standard list operators. Okay, so that's another kind of beautiful thing here. You write this thing that looks like a mathematical notation, right? Give me all the x from this where, but it's just syntactic sugar for something that uses standard operators like filter, let declarations, and this is concat map. This is just map that kind of flattens the result. Doesn't really matter what these operators are, but the thing is, you start with this comprehension notation, you remove all the syntactic sugar, and you end up with a normal functional program. And this is the brilliance of Phil Wattler, who saw that these operators here don't only work on lists, but they work on any kind of collection. And those any kind of collections correspond to so-called monads that the mathematicians kind of invented for all kind of other reasons. So there's kind of another nice deep connection. So in Haskell, which is completely pure, here's how you do I/O. If you want to print something on the screen, you do put string, whatever, and this thing has type IO of unit. So a side effecting operation returns a collection, which is kind of weird, but it's a very special collection. It's a collection that just says this thing has an effect. So this notion of collection is very, very general. Okay? But now what you can do is you can write something which is very similar to this list comprehension notation, but now you do the Yoda style where you put the kind of select at the end, but it's still the same notation. And you can translate this guy into these standard operators. So instead of having the kind of filters and so on, you can translate any comprehension, any monad comprehension in these operators. Okay? So it's just syntactic sugar over the standard monad operators. And the nice thing in Haskell, which is something that hasn't percolated through the real world, in C# and VB we now have generics, and everybody thinks, oh, generics is so great because I can now define a type that's parameterized by another type. But that's just, that's for the kids. What you can do in Haskell, you can parameterize over a type constructor. So you can have kind of higher order parametricity. Look at this. Here, monad M, and M is here used as a type constructor. So I can instantiate this with list, and then I get list comprehensions. I can instantiate M with IO, I get this. I can instantiate this with exception. So this is something very powerful that is not yet in the generics that we know of. And if you look at ML, they also didn't even understand this. They don't have higher order parameterization. But this is essential in order to capture this pattern that you can do this for any kind of collection. So that's important. And we will see later that we cannot express that in the type system of C#. Okay. So, as I said, we can have all these kind of different examples of monads. So what we did in Haskell DB is we defined a query monad. And what is a query monad? Well, that's a collection that's represented by code that when you execute the code, it will return the collection. Well, so again, it's a piece of code that when you execute it will produce a collection, which is really another collection, but it's kind of a deferred collection. That's an instance of a monad. So we could write comprehensions like this that correspond to SQL queries like that. It does look a little bit funky because in order to make kind of, these kind of deferred executions from constants, we have to lift them explicitly because Haskell doesn't have anything to do kind of meta programming, so we had to do that by hand. But the idea is that this was a monad that would remote the queries to a server. All right. So then the other thing that we wanted to do is to create all this XML stuff. Well, what we did is we introduced this notion of XML literals with holes like ASP.NET. And then, again, this would be translated into a universal representation. And again, you could arbitrarily nest XML with normal values. Okay, and if you know xQuery or any other language, it's very similar to this. Okay, but as I said, that was all theory. You look at this and you say, do I understand this? No. So when I came at Microsoft in 2000, Wolfram and I kind of, started this thing, and then we said, let's take C#. Let's drop this stupid Haskell thing. Nobody understands this. Why are you always... Let's take C#. Let's take a real language. Okay, so we took C#, and then we grew C# by making the type system complicated. So I hadn't really drank the Kool-Aid of making things accessible to the masses. I drank half of it, right? This was the right choice. Well, it wasn't even the right choice. I think this should have been Visual Basic. But here's where I went wrong. By saying, oh, let's do some more complicated type theory. Let's add streams, tuples, union types. Oh, and look how smart I am. I can do all these complicated types. So here's, the type system that we added in C omega. So this is the normal C# type system. So a type is either a nominal type or an array. So this is pre-generics, kind of really very poor, right? If you look at the type system, it's kind of, you just have this. There's not a lot of structure in the type system. So what we did is we added all these types. We added closure types, we added union types, we added intersection types, we added stream types, we added anonymous tuples. And oh man, how smart did I feel to have all the subtyping rules and stuff like that and making sure that it works. But did my mother-in-law understand this? No. So, didn't work. But there were some good things in here. So apart from the kind of complicated type system, there were some nice things. For example, in C omega, we could write comprehensions using SQL syntax. Okay, so you could write select, from the inbox where the from field is, some value, and then just return the subject, which would return a collection of rows that have a subject, optional subject. So here you can see how the type system works. We introduced another thing in there that you will now see in C# MVB, something called type inference. So you could say for each R in some collection, and I don't have to specify the type of the thing there. Okay, so this is a funny thing. If you look at languages like ML or whatever, they've been doing type inferences for ages. But in our mainstream languages, we still say, look at this. String n equals hey. You see that this is a string. Why do I have to say it there? Okay, so that's how simple type inference is. Look, you look at here, you see, oh, it's a string. Why do I have to specify it again? So that's kind of some slight thing that we took from programming language theory, and be careful, and added to the language kind of on the side. Here's another thing where I do think that type theory pays off. Something called incoherence. Here's the problem. Suppose I have a value of type t, and we introduce this nullable type. Because if you're dealing with databases, well, in SQL you have nullable types, right? I can have a nullable string that signifies that the name, for example, is absent. So suppose I have here, say that t is int, and now if I go from t to nullable of t, well, I have some representation to distinguish between the fact that the value is there or the fact that the value is not there. Okay, so let's say that we just kind of, put this guy in a box. Now, when I go from t question mark to object, what happens now? Well, if you go to object, you box the thing, right? So now suddenly I have kind of a double thing here. And what happens if this guy would have been significant, would be modeling null? Well, in that case, I would box it into something that wasn't null. So, whereas if I would start here and I go here, I get back, I box this thing directly. So, going from here to here or from here to here directly would give me a different value. Okay? And this is called incoherence. A coherent type system, it doesn't matter if I upcast this way or upcast that way, I always end up with the same value. But here, I end up with either a boxed integer or a boxed nullable integer, which is not the same. Okay, so it's incoherent. And what you have to do is, when you're boxing a nullable to object, you have to unwrap the value, and if this thing represented null, you have to map that to the null pointer. Okay, so, and Wolfram and I spent, I don't know how long, right? We even tried to throw in tier improvers to prove that our type system is coherent. But anyway, the great thing is that very, very late in the Whitby shipping schedule, finally people realized that this is a real problem, in practice. Because in the BCL we introduced this nullable type, but it was incoherent. If I boxed a nullable, or if I would go directly, I would end up with two different results. So, like 2 months before Whitby shipped, there was a kind of a push to make the type system coherent. And what happens now? If you box a nullable, it gets unwrapped. So this is a great thing that we took directly from this arcane programming language theory. Who knows about coherence? But if you look now deep in the CLR, in the JIT, this happens. And thanks to, crazy theory guys that they kind of study these things and try to prove that their type systems are sound. So I think this is the kind of one gem from all the complicated type systems that we did here. But I think it's a very important one. Okay. So much for C omega and how it kind of, influenced, the CLR at a very, very, very fundamental level. Let's now go to the LINQ project. So this is the continuation of that, where we are saying, look, we want to add these kind of capabilities to the mainstream languages like C# and VB. So how do we do that? Well, if you think back of these monads, what we did there is we said we have this comprehension notation, and you can use that you translate that into kind of standard operators. Okay, so now I can use the same query notation to query over any collection. So we do the same here. We're defining a framework that has some standard query operators. Okay, and then we have some domain-specific libraries. So this is like standard monadic operators. We have some domain-specific libraries for relational data, for XML, and then all these languages here can define their own syntax for comprehensions that map into these standard query operators. Okay? But don't be fooled by pictures like this. What LINQ really is adding monad comprehensions to C# and VB. Okay? That's what it's about. It's just, Haskell in sheep's clothes. All right. So here's an example. In C#, I write from C in customers where state is Washington, select new, name phone. And this is translated by the C# compiler into standard query operators, filter and map, just as we knew from functional programming. So there's nothing new here. But look at this. C# does type inference. I don't have to write the type of contexts. Okay. C# now even has something called lambda expressions. I mean, every time I hear Anders say in public lambda expressions, I say, yeah! Okay. And this looks even like ML, right? So it's, it's really cool. No func? No, it's not necessary, right? There's one interesting point here, is that we say we have type inference, but it's very subtle because we need to have type inference. Because look what this guy returns. It returns new name phone. There's no type name there. Right?
Put a type name there?
You can put a type name there, but that's not interesting. It's interesting where you don't put a type name there. Because what is the return type of this thing? It has a return type, but I cannot say it. It's not denotable. It's expressible, but it's not denotable. I cannot pronounce it. Even if I would want to write the type of context, I couldn't, because I have no notation for these tuple types.
But you can still express the concept of one of the sub-elements.
Sure, I know that it has a name field of type string,
right,
but I cannot write down the type, so we're forced into type inference. So that's the funny thing. So these types are expressible but not denotable. Why? Why? And this is because the CLR only supports nominal types. So there's no way in the CLR to make structural types, because what can you do, right? I can create a nominal type, but now the kind of scope of that type is within an assembly. So if in assembly A I define a type which has string name and int phone, and in assembly B, these types are not compatible. So it's impossible in the CLR to have structural types. In C omega, what we did is we said these guys are structs, so we could have value assignment, so we could kind of, but if they're reference types, you lose object identity. So that's kind of, another source of hair loss is how to implement structural types that maintain object identity in the CLR. I don't think it's possible. So we're kind of forced to do type inference. In Visual Basic, we're planning to allow you to write down this type. But in VB, we erase to object. And then since VB allows late binding, you can still access it. So VB gives you a little bit more wiggle room because it supports late binding. But in C#, it's more difficult. So that's type inference. Lambda expressions. Notice here also that I didn't write the types of the arguments of the lambda expressions, right? So we do type inference here also on the argument types here. And again, if you look in the C# tree spec, it's kind of a very interesting inference algorithm. And then the other thing, the main important thing is that this is just a syntactic translation, just like monad comprehensions are taken from this into this standard operators, that's the same happens here. Okay. Well, if you were kind of paying attention, you would have said, Erik, what the heck are you talking about? If customers has type, say, IEnumerable of customers, it doesn't have a where method. But I still write customers.where. What the heck are you doing? You're fooling me. No, 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 no. This is another trick, which is called in the literature the expression problem. Right? It's the problem that if you define a class, it's easy to define new subtypes of that class, but it's hard to take an existing class and add new methods to it. Right? Because now, I cannot, maybe I don't even have the source code of that base class. In a functional programming language, it's easy to define new functions on a given type, but it's very hard to add new alternatives to the type. If I have type list, I cannot just add some new subtype to that. So it's like, either you have extensibility this way or you have extensibility this way, but there's never extensibility in both directions. With extension methods, we kind of get a little bit towards solving the expression problem as follows. What you can do is you can define a static method and then mark the first argument with this special modifier this, and now you can use that thing as if it was an instance method on that type. Okay? So it's just a kind of trick to make it appear that IEnumerable of t now has a where method. So you can now write this using instance syntax. The compiler will first try to do normal name resolution, then it will try to find one of those special methods here. So in this case, this will resolve to this static method. So there's no instance method, so there's special magic here. But I think this is kind of a very nice way. It's kind of a very cheap way to add new methods to an existing type, which has been a general problem. So here, along the lines, we kind of solve some of the big open problems in computer science. Well, we don't really solve them, but we give very pragmatic solutions to them. So here's another thing, and this I think is truly beautiful. I still write the same query, okay, but now suppose customers now has type, say, table of customer, and table is another kind of collection, right? It's a parameterized type. But now look at this. Table inherits from IEnumerable, but look at this. The where method now, instead of taking a function, I should say that here too, func t of bool is a generic delegate type that takes a t and returns a bool. So this is our way to kind of write structural types, okay, by just using generics. But look at this. In this case, it says expression of func. So this is one piece of magic that's built into the C# compiler. So this lambda expression here, okay, can be converted either into a delegate or into an expression tree that represents that delegate. So you can get an intentional representation of that delegate. So you can do meta-programming. If you know Lisp, you say, oh, in Lisp I can do that, but quote and quasi-quote. But there you have to kind of, explicitly quote your things. But here it's based on the type. So this lambda expression has no type. or it has a type that I cannot say. Okay, but it's convertible to either a delegate type or to an expression of a delegate type. So again, there's some magic here.
So I have a question. Have you done studies and seen what programmers think of this, and can they program against this?
So that's a good question. So one of the things is that you have to distinguish two sides here. The API writer has to be very careful. He has to decide whether he wants to have a representation of the delegate or just the delegate, right? So he has to decide whether he wants to have an intentional representation or not. From the user's point of view, it doesn't matter. Right? I don't see here whether I pass in a delegate or not. So that's the beautiful thing here. The user just writes a lambda expression. The API writer can decide whether they need to have an intentional representation of the code or whether they just have to be able to call it. So I think that's a very powerful thing.
Intentional representation, does it mean you have a complete object model for expressions and everything?
Yes. So it's look at this. Expressions are capture everything that's in the IL. So what happens is the fully resolved parse tree, or it's not parse tree anymore. It's just kind of the semantic tree from the compiler that you get. So all overloading has been done, all method calls have been resolved, and that's what you get. So it's a full object model. Yep. So that's a beautiful thing. And if you look here now, if I go way back to the ugly Haskell code here, since we didn't have this kind of automatic type-based metaprogramming, I had to kind of do this by hand. I had to quote this by hand. I say, look, I don't want the string. I want to have an expression that represents this string. Okay, and I couldn't write .sit. You know, I had to say, I want to have the expression that represents. But now this is all nicely done under the covers based on the type. So I think this is a major innovation that I haven't seen any approach where people use the type to kind of convert either to a delegate or to an intentional representation of the code. But this opens up, if you want to do metaprogramming now, C# and VB are your friends, right? You don't need to go to Lisp anymore. You can just use, your favorite programming language. Okay.
I mean, this duality that you've got between essentially a closure and an expression seems a little confusing to me, because when you build a delegate, you're allowed to capture things that are in scope. But that notion of scope doesn't have meaning when you're just passing a piece of text.
But you're not passing a piece of text. So your question is good, your conclusion is wrong. Okay? So what you're saying is, what happens if, say, inside this lambda expression, I would refer to something in the context? How is that captured? Because in a closure, that's kind of captured in the context. Well, we capture the same thing here. We built something we called a funclet. So what we do is we determine the maximal free sub-expressions, if you know something about combinator implementation of functional programming. So you look at the largest sub-expression that doesn't depend on the argument, and you capture that in a little thunk. It's like a zero argument function. And now when I give you this expression tree, in there are little functions that you cannot see because these are values from the context. So if you want to get that value, you evaluate that function and you get the value. Okay, so it's like a closure.
So somehow you managed to feed that whole thing over to SQL.
Yep, exactly. So what we do is we take these expression trees, we compile them to SQL, we run them in SQL, we get back the results, we use this thing to kind of create the objects and give you back. Exactly like the Haskell DB query monad that, from 5 years ago, 10 years ago. Okay, but that's the trick. I can now give you a representation of this delegate that you can now compile. Maybe you have a GPU and you want to evaluate this. Well, you compile that to whatever. So this is very, very, I think, very powerful. We have just seen the beginning of this, of using this.
Except on my GPU, I have no way of calling your function. I mean, I can only...
No. You do that. You do that when you generate the code, right? Because once you remote, that's when you evaluate the funclets. You can do more fancy things where you kind of start to, and if you look at the guys at CMU, they use kind of modal logic to describe where these things live. So you could kind of, instead of evaluating this here, you could have a little proxy that when you remote, it would call back to get the value, right? So just your imagination is the limit. But the thing is, these things create closures that capture the context. Okay? So here are some kind of small things that we needed to do. I already told you about these anonymous types. So I can create new instances of anonymous types. Or I can use a named type. And the thing is here, in normal C# and VB, in order to create an instance of an object, you have to use statements, right? You call the constructor and then you set the fields with kind of new sub-expressions. But in these queries, we have to go to a much more expression-oriented style of programming. So what we allow you to do here is to create complicated, I should point here, complicated object instances in an expression-based syntax. So instead of using, a sequence of assignments, I can just use an expression. And here's something other very interesting. Here I create a new person. I set the name to Joe, age 242, and then I have an address. But because I know that I'm creating a person, I now know that the address field has type address, so I can infer the constructor. So I don't have to say here new address, because the compiler knows, so it's kind of the dual. Instead of doing type inference, we're doing code inference. So you don't have to say new address here, because the compiler can infer that. Okay, so that's another thing. So you can write very concise expressions where the compiler infers the type or it infers the code, depending on the context. So these are all nice little things that you get for free.
How do the error messages look like? Like if the compiler cannot infer something, like in Haskell? Or?
Oh, that's in Haskell. This is my favorite hobby. You write a 2-line program, and you get the 1,000-line error message. Cannot unify 500 screens with 500 screens, and then somewhere deep, there's the difference. Type inference here is much simpler. We don't do any of this unification crap. It's local type inference. We only look at the type of the right-hand side, and that's what we assign. We don't look at all the uses of this variable. So there's never unification. It's pure local, bottom-up type inference. So the error messages are much easier. So because you never have this kind of thing that flows from various sides. Okay. Now, in Visual Basic, the syntax for these comprehensions is, I think, the way God intended queries to be. It uses SQL syntax. So instead of saying from where select at the end in the Yoda style, you put it in front. You say select name phone from CN customers where state equals Washington. Okay, so we have there the kind of stay as close to SQL syntax as possible.
I've seen a video where Anders makes a big point about it having to be in the Yoda style.
Exactly, so that's why I make a big point that it should be in this style.
But I've written parsers for SQL, and you can have it be either way.
Sure. Yes.
Oh, that makes sense.
Okay, so here. Okay, so my reasoning is, the thing is, I want to read these queries. If I think you should program for the reader, not for the author of the program. If I read a query, I usually just want to see what does this thing return. Oh, it selects name and phone. And usually I don't even look, how that's done. Okay, but if you put this at the end, and even if you like group by and having and so on, then this guy comes way at the end. So now to read it, I have to kind of scan all the way to the end. Oh, that's the result. Right, so for reading it, this is much more natural. And this is the way mathematicians have been writing that, right? Mathematicians write this. X, where X in X's such that P of X. Select from where. So we're just, mathematicians are always right. So why do we even question that?
Mathematicians also write universal quantifiers, which are written in a different order than that one.
Sure, we just ignore the things that we don't like about the mathematicians.
Our argument was about the inheritance. The
Yes.
syntax enables that.
Yes. So we believe in the VB that we can get IntelliSense working for this too.
Yeah.
It's just the way how you navigate through these different classes. Because even if you put select in the end, say, and now I do a group by or something in there, I still have to kind of go, up and down this thing. So the IntelliSense, I think that's for me a little bit of a red herring. I think I like this, and I think we can make it work. And if not, as you say, there's no reason from a syntactic perspective why this cannot be, or you can support both, yes. And then the other thing in VB, we have parity with all the other features that I showed you, like anonymous types, object initializers. And the difference is that in VB we are thinking of having denotations for these anonymous types. Okay, so now let me quickly talk a little bit about the domain-specific operators. So D-Link is now adds on top of this basic infrastructure support for accessing relational data. So what you do is you write this query, and D-Link uses this fact. Well, first of all, this query here is translated into the standard query operators, right? Just like syntactic translation, this comprehension is translated there. But then we use the fact that we have expression trees that we then translate to SQL here, okay? So for D-Link, we remote these queries to SQL. And this is where this notion of expression trees comes in handy, okay? Then it's executed here, you send back your rows, and then, because we know all the types, we can create all these objects. And then in the middle here is some infrastructure that's kind of typical. Look at any OR mapping, Hibernate, Enterprise Java Beans, wherever that does things like change tracking, right? Because I get all my objects here, I mess around with that, then I want to submit changes, so I have to kind of track changes. You have to maintain object identity. What happens if I do 2 queries and I get back things that have the same primary keys here? I don't want to create 2 different objects. So this is kind of basically all kind of standard OR mapping stuff is in here. I think if you look at all these things, they are, mostly the same. The details differ, where do you put the mapping, and, how does the API look like, but they're trying to solve all the same problem.
I don't really see how the expression tree is much better than just sending the MSIL to the SQL set.
Very good question. Couldn't you, because MSIL is an intentional representation of code too. But the thing is, MSIL is too rich, right? Because now I can send arbitrary computations there. With the expression trees, we can kind of, limit the kinds of things that you can send. Think of it as like verifiable code, and this is remotable code. And with these expression trees, we can restrict you to writing remotable code. But in theory, there's nothing against sending the assembly across. And I've been arguing for that several times too, because we already have. But the thing is also, from the IL, now you have to decompile the IL, right? Whereas the expression trees give you at a much higher level of abstraction. So it's kind of easier to translate expression trees to SQL than IL to SQL. But in theory, it's completely possible. There was a question here too, or?
Secondarily, if they sent the IL, then it might be much more difficult to write something besides D-Link. Like if you're writing your providers that can satisfy the LINQ queries, it can be generalized.
Well, but the thing is, you have to be a little bit careful, because in here, these, like in the where clause, that can be any arbitrary C# expression, right? Which can be very complicated too. So, so there you can even write things now that you cannot remote to SQL. And then the D-Link infrastructure also tries to kind of tease that out and say, oh, I cannot remote that. But you can imagine that it's very smart. It says, well, I can remote this, but I have to compute this here. So this, in general, these providers here are not very simple, okay? Because they have to deal with a lot of, plus generating SQL from arbitrary queries that can be nested and so on is not easy. because SQL is...
I'd agree with that, but if they had to actually take IL and work with that, it'd be even worse.
Exactly, yes. But, you know, difficult or really difficult, maybe, you know, it's idempotent, I don't know. But yes, right now we think that it's easier to do it with expression trees. All right. So, as I said, this is kind of a typical OR mapping thing. What we do at this point is we do mapping using attributes. And then, of course, there are lots of people that say, oh, we want to do the mapping using some external XML file. But then I think, you know, gee, if I do it with some external XML file, then I have to solve the versioning problem. I have to know that it's like, you know, who created that? Oh, we already solved a lot of this with assemblies. So why don't we just use assemblies and custom attributes? So I think, personally, I think this is a good thing. But again, I'm just an amateur in this, and we're doing this such that our customers can tell us what's the right thing. This is, you know, change tracking. And then the other thing is that this is all built on top of existing APIs. So really, it's kind of syntactic sugar on whatever is already there. There's nothing new here. It's built on top. Okay. The last domain-specific library I want to talk about is the XML one. And this is another kind of big, you know, embarrassment. Because the way we tell our customers to use XML is horrible. So I don't know about you, but I don't know what this program does. Okay, it's like lots of imperative assignment statements and so on. But this program creates an XML document. Okay, using the DOM. In Dutch, DOM means brain dead, which I think is a very good name for the DOM. It's brain dead. The DOM, the XML DOM, is a prime example of design by committee. So it started out as the kind of, you know, object model for dynamic HTML, and then some guys got together and said, let's generalize this for arbitrary XML. And, you know, because there were people from Microsoft and IBM and Netscape, you know, let's kind of bargain a little bit. And what you get is some really, really horrible API, extremely imperative. It's just, don't talk about it. So, but the most important thing is the following. First of all, it's imperative construction. And as I said, for these queries, we need to create values in an expression-oriented style. That's why we introduced object initializers. Well, if we cannot create XML in an expression-oriented way, we cannot create XML results from queries. So the DOM is kind of already is out because of that. Another thing that you see in the DOM is that you cannot create elements by themselves. You have to always create them in the context of a document. So this is really weird. The DOM should be about XML, where XML should be first class, right? I should be able to take an XML value, pass it to you, you should be able to do something with it, pass it to somebody else. But in the DOM, it's not a first class citizen, because XML can only live in a document. And if I want to take it out of a document, now bad things happen. So I really cannot understand. And this is what we tell our customers to do. Ah, man. They should come here with bombs and kind of, you know, burn the buildings that we're giving them this and nothing better. But we're doing this, we're working on it. So in the whole LINQ framework, we now have the XLINQ API. So you create the same document or the same XML that I showed you before by an expression-based construction. So I can say new X element, item, new attribute, and it has child element. So you see here that it's much simpler to create XML. You just write expressions. The other thing is there's no document scope. Okay, so these elements are first class. You can pass them as arguments, you can return them. They don't have to live in a document. What we do is if you create this element here, and now I pass it around, and it's not parented, we will just use it if it's already parented. So if I write a query that kind of takes this guy, we will clone it for you and reparent it. So these things are completely first class.
I know you were trying to convince me to convert to Visual Basic. I haven't done on that yet, though. Does underscore mean what I think it means?
Yes. Visual Basic, this is from the time that it was still kind of an interpreter where you typed in line by line. So you have to tell it that your line is not finished yet, right?
Come on, man. Get rid of that thing.
Yes. We're planning to get, but it's kind of quite hard to get rid of it, actually. But we're working on that. Okay. We're working on that.
Good.
If that's your only concern about VB, you know.
No, you were making a case that you love case insensitivity.
Yep, that's another thing. But yep. But actually, I use VB syntax here, but this is how you would write it in C#. Right? Also in VB, but in C# you have to do it like this. In VB it will be much better in a couple of slides, so then you don't need these underscores.
Do you like it because it has enough end parentheses at the end for a functional language?
Well, that's the thing. You shouldn't confuse Lisp with a functional language, right? But yes, I don't like these parentheses, you know.
Yeah.
This is what I want to write. Because if I'm dealing with XML, I want to see XML. So in Visual Basic, we can write this. You can just cut and paste XML. Okay? XML is a first-class value that has a literal notation. And then, again, you can leave holes using this ASP-style notation. And then I can put in a nested query. That in there can have an XML literal that has a nested query again. So this is the VB style of doing XML. Okay, and again, the compiler takes this and translates this into calls to the underlying API. But I think this is kind of the level of abstraction that you want to work with XML, because I don't want to see strings. Whenever I see quotes and strings, I get nervous. This looks ugly. It's much better than this. Much better than this, but it's not good enough, right? This is good. So, and you see there's no line continuations here. So, but yeah, so in VB, we have very, very deep XML integration. Another thing that we add in VB, and this is something that, you know, this is kind of completely orthogonal to the whole links discussion. There's kind of a lot, if you look in the blogosphere or whatever, people saying, oh, dynamic languages are so great because they're more flexible, blah, blah, blah. The problem is that people think too black and white. If you look at dynamic language like PHP, Python, Perl, they throw away all the types. Then if you look at a statically typed language like Java or C#, they say, oh, everything has to be statically typed. Visual Basic is unique in the sense that it says, look, if you want to use static typing, go ahead. If you want to use dynamic typing, go ahead. And you can mix them in your program. So you can use static typing where possible and dynamic typing where necessary. And one of the things that the way VB does that is by doing late binding. So let me just use the whiteboard here. If I say dim x as object, and now I can say x.foo. So if the static type of the receiver is object, I can call any method, I can access any member, and the compiler will use late binding. So in some sense, it's kind of funny. The late binding in VB is driven by the static type of the receiver, okay? Because the static type of the receiver is object, it enables late binding over object. So what we're doing in VB9 is we're generalizing that, and we're saying if the static type of the receiver is an XML type, then we're doing late binding over XML. Okay, so it's kind of late binding, but driven by the static type of the receiver. So we're kind of really using, you know, we're leveraging static typing here to do late binding. So in VB, I can write build2.street, and since if build2 is an XML type, like X-element or a collection of X-elements, the compiler will use late binding and say, oh, I have to call elements of street. And this is what you have to write in C#. Still strings in VB, you just write it as a normal member access. And then we have the attribute access, build2 add country. If this guy has static type XML, the compiler will translate it into this. And we need IntelliSense for PowerPoint, because there was a typo there. Okay, and then we have a descendant access. So if you write purchase order ... item, it will say give me all the items no matter how deep. But the trick here is that we are using the static type of the receiver to implement the late binding. I was at Uppsala talking with the Java guys. So the Java guys are also thinking about adding XML to Java. And they told me, oh, we like this VB approach, and we like this late binding. And they are saying, they are going the other way around. They say, oh, now we generalize late binding over XML to late binding over object. So they were thinking of doing this. If I say dynamic x, then you can say x.foo. So I wouldn't be surprised if a future version of Java would have dynamic late binding in the style of VB. The scary thing is that the Java guys are also thinking of adding a new bytecode instruction to do efficient dynamic dispatch. So I think there's a very interesting arms race going on between the Java world and us, and we're kind of, making progress by kind of progressing in chunks.
So what about the divergence of VB and C#? Because the word on the street has generally been, it's converging, but what you're saying is they're going off in pretty different directions, it seems.
Yes. So here, let me kind of, of course this is all recorded, so I don't care. I'm in both the C# design team and the VB design teams, and I think it's good that the languages diverge. Because what good is it to have two languages that are just syntactically different? I think VB has a kind of, should cater for it's the working man's programming language, right? And think.
So I can think of it like this sort of, if I look at the personas, you're enabling a lot of cut and paste with VB. Like take your XML from somewhere, just paste it into your VB, do a little muckety-muck, and boom, it's it's there. Whereas in C#, it's not going to it's going to be more programmatic.
Yep.
In the object-oriented.
Yep. So and then the other thing I think where I think we can really make the languages different is by leveraging the fact that VB has this late binding, right? Because I think that's a space where there's no language currently. It's like either you're statically typed or you're dynamically typed, but there's nobody in this space, which is very interesting. And I think there's no research about it. All the researchers, I mean, if you want to get your paper published in POPL, it has to have type soundness proof and whatever. But nobody talks about this kind of this interesting space between static and dynamically typed, which I think is where VB lives, and which is, it's a gold mine. For example, here's another thing. And this is type classes. If you know Haskell, there's something called type classes. So in VB, we want to introduce something which we call dynamic interfaces or duck typing. But really what it is, it's type classes. So here's the following. Suppose I have an XML document, but I want to access that in a strongly typed way. So I want to express the contract. I want to express the intention that this document has a street of type string and a country of type string, and this should be item here. Items of type I number of items. So I want to specify my kind of a contract that if you give me this element, it has these properties. So one way you can think of that is I define this extension of X element, customer, that has these properties, and now I can cast an X element to a customer, and now I've told the compiler, look, I assume that this thing has these properties, and now I get all nice IntelliSense and type checking, but it's all based on this kind of compile time cast. It's like it's a view over X element. It kind of expresses the contract that this X element has these properties. Okay. Yep.
Same as C# extension methods?
In C# extension methods, what you do is I could define an extension method. So I could define, static class foo, which has, you know, string, and what do we have here? Street. And then I could say this, you know, X element, you know, source. But the thing is now, this works for any X element, right? But what I want to say is I want to be able to kind of express statically that if you give me a customer, then it has this. So in some sense, C# extension methods are anonymous views, right? They work for anything. If you compare this with Haskell type classes, in Haskell type classes I can define this contract, and then separately I can define an instance. But then I have to specify a witness. I have to tell you this type implements this contract in this way. And now the compiler does a compiler transformation where it passes to every function as an implicit argument the witness for that contract. But here we are saying we only have kind of default implementation, so you never have to do dictionary passing if you know a little bit about Haskell. So you don't have to pass around the witness at runtime because it's really all based on compile time cast. So again, we're trying to take this kind of complicated thing from type theory, simplify it such that my mother-in-law can use it. And I don't know if she's up to this, but this is definitely one of the more experimental things that we're kind of looking at. Okay, that concludes my talk. So I hope that you've seen here that, you know, we have been able to take a lot of, you know, very esoteric programming language research, monads, type inference, type classes, all that stuff, coherence, and put them in these kind of mainstream languages. But it requires a lot of patience, right? The comprehension ZF things was from the 70s, so it takes many, many years. And the other thing is it takes ripening. So you have to take these concepts and kind of, you know, simplify them to make them accessible to the masses. Like type inference, yes, in Haskell is great. You do unification, most general types, whatever. But in practice, you know, that's too much. So you have to see how can you make it simple but still useful. And that's the ripening stuff. And the other thing is, I think what personally disappointed me is that if you look at a lot of programming language research, they abstract from the real problem. So, you know, you define this mini language that's all nice and you can do all your proofs, but by doing that, you have kind of, you know, glossed over details that are important. So you have kind of abstracted too much. So it requires still a lot of work to take these results and then apply them to practice. But again, that keeps me off the street. But anyway, that's it. If there are any questions, I'm happy to answer. So by the way, this is all you get. This is all previews are available. So if you Google for LINQ, you will find links to this, and you can, you know, play with it. It all works on the Whitby builds. So.